Hello, everyone. Good afternoon, and welcome to the American Floral Endowment's Grow Pro webinar series. I'm your moderator, Karen Schneck. I'm a member of the AFE's Young Professionals Council and a senior research specialist in live goods R&D at Scott's Miracle Grow. I coordinate the annual flower trials for the Scott's Miracle Grow and Bonnie Plants flower programs. I received my bachelor's and master's in ornamental horticulture from Kansas State University. Today's session is on effective energy control in greenhouses. On behalf of the endowment, I am excited to be a part of AFE's Grow Pro webinar series that features a new topic every month, presented by an industry expert. The webinars are free to everyone thanks to generous support of AFE's sponsors. If you'd like to learn more about the webinar series, or if you are a supplier and interested in becoming a sponsor for a topic, you can find that information on AFE's website at endowment.org/GrowPro. Today's session was pre-recorded in English by Dr. A.J. Both. After the presentation, Dr. Both will join us for a Q&A. Feel free to submit your questions through the Q&A feature or chat at any time. We'll answer as many as we can before the end of the hour. Unanswered questions may be answered through a separate email exchange. This session is being recorded and will be shared to AFE's YouTube account. Through YouTube's accessibility features, you can access closed captions in other languages. To get us started, I'd like to share a bit about today's expert speaker, Dr. Both. A.J. Both is a professor and extension specialist in controlled environment engineering in the Department of Environmental Sciences at Rutgers University. His research focuses on methods and systems to provide the optimum growing environment in protected plant production facilities and includes topics such as hydroponics, supplemental lighting, crop modeling, and the use of energy in agricultural systems. He also serves as a consulting editor for publications by the American Society of Agricultural and Biological Engineers and the American Society for Horticulture Science. He is involved in the development of professional standards that address the design and operations of commercial and research plant production facilities. Dr. Both, welcome and thank you for presenting today on effective energy control in greenhouses.
Good afternoon. My name is A.J. Both. I'm a faculty member at Rutgers University, and I'm going to talk today to you about effective energy control in greenhouses. And I want to thank the American Floral Endowment for giving me this opportunity to communicate with you today. And the first image you see in this picture is an image of a greenhouse with a thermometer showing in the front. And of course, a thermometer is a very inexpensive measuring device. Very useful, but only useful when you look at it, and it cannot record conditions. So it's only useful at the moment you look at it. And so I'm hoping with this presentation to impress upon you that we can use more advanced technologies to improve our control as well as reduce our energy consumption. The first slide is showing you then what I think are things worth considering when you are concerned about energy consumption in greenhouses. The first step that growers typically should be doing, in my opinion, is they should investigate where they can conserve energy. So what particular systems are they using that could be modified or adjusted or perhaps changed so that they can reduce their energy consumption. So conservation is typically the first step that we recommend growers look into. And then the next thing you may want to do is to have an energy audit. You can do that yourself if you know how to do it, or you can hire professionals that are trained to do energy audits. And they basically review the entire facility and look at all the equipment, all the energy uses that are going on, and try to come up with recommendations for how things may be changed or how things could be improved to reduce energy efficiency and reduce, therefore, the energy bill. You also may want to look at high efficiency equipment. The technology has advanced in recent years quite significantly. And even if you have recently upgraded with some new equipment, you may be surprised that there are even newer equipment available that has an even better efficiency than what you already have. And of course, when you go that route, you can significantly reduce your energy consumption. You may want to think about adjusting your environmental set points. If we reduce the temperature set point, or we reduce the amount of lighting that we want to add to the crop, we can reduce energy consumption, but clearly that will have an impact on the crop. So you have to be careful when you make those changes. You could consider alternative fuel sources. They are in some cases cheaper and in some cases locally available, but you always have to worry about long-term changes. That fuel may not be always available in the long term, and so you might want to consider carefully before you switch to a new fuel source. You may want to switch from high-pressure sodium lighting to LED lighting. In most cases, that can result in a reduction in electricity consumption, but as you probably know, LED lighting systems are typically more expensive to purchase, and therefore the initial investment is typically larger than if you go the HPS route. You may also want to think about avoiding or reducing your winter production. When you don't grow a crop in your greenhouse during the winter months, when it's cold, you don't have to heat it as much, and therefore you can save energy. But of course, that's going to impact the overall return on investment from your facility, and that may or may not be a good strategy. As an engineer, we always like to look at the environmental control system, and the sensors are a key component of that. And it's always a good idea to calibrate or recalibrate your sensors to make sure they are recording the conditions that are actually occurring in your facility, so that the control system makes the right decisions based on the right information. You may want to think about expanding your computer control system. The advantage of that is that the computer control system can do many more things and can do many repetitive tasks very accurately, much better than us humans can. And therefore, you can, using computer control, reduce energy consumption and make your system more efficient. And then if you have computer control, it's a good idea to regularly review your data logs to understand how your system works, where you may be able to implement changes to try to improve the overall efficiency. I want to go through some key areas where I think you can gain some advantages by being very conscious about energy conservation and reducing your overall expenses in terms of your energy use. The first one is equipment maintenance. Here you see a crew cleaning a boiler, an important step in the process to maintain high efficiency of the boiler system. And of course, this is not only necessary for your boiler system, your heating system, but also for other systems you have in your facility. When you can maintain your equipment well and regularly, you will very likely reduce the number of breakdowns, and the breakdowns, as you know, typically occur at the most inopportune moment. And if you have those breakdowns, it's costly to repair during those times. And of course, breakdowns will reduce your overall efficiency because things have to be repaired and things may not be running under optimum condition during that breakdown. So keep an eye on maintenance and make sure you have a regular schedule to do certainly the most critical things in your operation. Another good investment for when you are considering reducing your energy consumption is an energy curtain. And here you see an example of an energy curtain that is in the process of being closed at the end of the day. Typically, these curtains are fairly efficient in reducing heat loss during the night and during cold days. And they can also do double duty by during the summertime when we have high light conditions, function as a shade curtain. And in terms of energy conservation, it's not unheard of to see reductions in energy use of 20 to 30% when you have these curtains installed. In this particular case, there's only one curtain. There are some greenhouses that have multiple curtains. For example, one could be optimized for the shading task, one could be optimized for reducing heat loss, and even a third could be added if you grow a crop where you want to adjust the photoperiod. So a blackout curtain that reduces or eliminates any light coming in from the outside. But of course, if you add multiple curtain systems, you're going to increase the price of those systems. So typically growers have one curtain, and that then serves these two purposes, shading as well as energy retention. Another smart idea is to look at your ventilation system, and particularly when you have a mechanical ventilation system with fans that pull the air out of the greenhouse. If you look at the insert on the upper right-hand side, typically we have mechanical louvers that are made out of metal, and over time that metal may not be closing properly anymore. Things get bumped and bent, or small openings may over time develop in that system, and you get air leakage. And with that air leakage, you can get energy loss, of course. And so the big picture you see in this slide is showing you a roll-up system that once the fan is turned off, that roll curtain will come down and forms a very tight seal around the opening. So as long as the fan is not running, that seal is closed, and there will be very little air exchange between the inside and the outside. And as a result, we have very little energy loss. So a good idea to consider. Another interesting idea is an image you see here, a greenhouse grower who was concerned obviously about heat loss and decided to install bubble wrap on the inside of a north-facing side wall. And the bubble wrap is interesting because, of course, if you're thinking about energy conservation and energy reducing your energy loss, you could also install opaque insulation board in that wall to try to reduce your heat loss. But when you do that, you also cut off the light transmission. And so this was an attempt to not only install a layer of insulation, but still allow a fair amount of light to come through. And you may think, why is that necessary on the north-facing wall? Because the sun is typically facing south. That is because during overcast day in the wintertime, the light is diffuse, and there will still be a fair amount of light coming in, even through the north-facing wall. So the idea of adding this somewhat transparent insulation material is a good idea. You could do two things at the same time. You reduce heat loss, but you also maintain light transmission. I mentioned that there are improvements in many different systems we run in operations, and certainly heating systems are a good example of that. First, I want to talk about unit heaters. Here you see an example of a unit heater installed in a greenhouse operation to try to maintain the temperature set point. This is a unit heater that operates on either natural gas or propane, and it's a type of unit heater that keeps the combustion process separate from the air volume inside the greenhouse. So you see two pipes on the top of the unit. One is the intake. The intake provides fresh air for the combustion process, and then after the combustion takes place, the exhaust gases are then vented through the second exhaust pipe. And this particular unit is also condensing the exhaust gases. In other words, it's cooling the exhaust gases so that the water vapor that was processed or produced during the combustion process is condensed from a vapor to a liquid. And that process actually retains some energy inside the facility before we expel that exhaust gas to the outside. So the overall efficiency of a system like this is pretty high, is in the 90s. And that, of course, is a very good number, because that means that the money you spend on the fuel is mostly converted into useful energy, useful heat for your greenhouse operation. Of course, these systems, because we are condensing the water vapor after the combustion process, and therefore we produce moisture inside the heater, the unit therefore has to be made out of materials that can withstand that moisture. So typically the combustion compartments are made out of stainless steel to make that work without having premature failure of the heating system. That makes the individual unit a little bit more expensive, but over the life of the unit, the added efficiency that you gain is typically well worth the additional expense of the individual unit. And keep in mind, if you do not have condensing boilers, then as you see in the equations here, when you combust either natural gas or propane, you will produce water vapor. And if you don't move that water vapor out of the facility, you get all that water vapor inside the facility. And of course, that can contribute to problems when that rises to levels where the plants get affected by high humidity levels. So it's a good idea to have separated combustion happening and make sure that any product of the combustion process is removed and never in touch with the greenhouse environment. We have similar high efficiency systems when you operate boiler systems. So now you're talking about a hot water heating system. Again, the efficiency can be very high and they work basically on the same principle. We capture the combustion gases and we cool them down. And we cool them down by running them through a heat exchanger where we exchange the heat in the combustion gases with the colder water that returns from our growing system. And you can see that laid out in the schematic on the lower right-hand side of this slide. The return water from the greenhouse operation is relatively cold. We run that by the hot exhaust gases so that water gets preheated before it gets introduced into the boiler system and gets reheated again. As a result, the exhaust gases will reduce in temperature, and as a result, we will see some condensation happening. If you have a very large heating system using this technology, you could use some of that water, for example, for irrigation. But typically the quantities of water that you produce are relatively small. So this is another example of how you could upgrade your heating system, especially when you use a hot water heating system, by using these high efficiency condensing boilers to try to reduce energy consumption and become more efficient. And I have some specs for these systems listed here. They're typically low mass, they're typically relatively small units. They don't need a large water reservoir because they operate on demand and therefore they have no standby losses. There's no water reservoir that you try to maintain at a certain temperature just in case you need some heat. They can deliver the heat very rapidly. And as I said, they are very small units and typically they have lower maintenance. Another interesting approach when you consider energy conservation and energy savings is to look at how you use your electric motors, whether they are for pumps or for exhaust fans. Typically, those systems operate either on or off, and that means that they're either on at full blast or they're not running at all. But it doesn't mean that they are closely matched with the demand that there may be, for example, for the ventilation or the amount of water you need to pump. So typically, those demands change depending on the conditions. We don't always need to run the ventilation system full blast. We sometimes want a little bit of ventilation, and the same is true for pumping water. We sometimes want just a little bit of water, not a lot. And so if you switch to a different technology called variable frequency drives, which is a device that regulates the amount of electricity and the type of electricity that we feed into fans and pumps, then you can match the output of the motor, the electric motor, exactly with the demand that you have. So if you need a little bit of ventilation, the motor will run at a lower speed that exactly matches the demand at that moment. And if you do that, then you can certainly save power consumption and therefore reduce your energy bill. But I have to point out that this technology is mostly used when you have three-phase motors, and that may or may not be the case for your operation. There are some variable frequency drives for single-phase motors, but they're not very common. Most common approach is to use it with three-phase motors. Another idea is, as I mentioned, to try to reduce your thermostats, to try to lower the set points. Of course, this is going to reduce your energy consumption, but as I mentioned before, you have to be careful doing so because it also can impact the crops that you're growing. When you grow your crop at a lower temperature, it's very likely it will develop less quickly, and you may have a delayed harvest time. So you have to weigh that consideration carefully before you implement it. You see in this example here, a grower who has a bunch of thermostats mounted on a piece of plywood. And I indicated with the numbers here what those thermostats are for. There are 3 stages of the fans, 2 stages of the vent windows, and another 2 stages of heating. And if you ever try to manage a system like this, you recognize that this is quite challenging in order to maintain the right conditions, as well as in an attempt to try to reduce your energy consumption. It's not inconceivable because these thermostats are not that accurate. You can see they have a big heavy coil on the bottom, indicating that they respond to the change in conditions fairly slowly. It's not inconceivable that these thermostats fight each other. In other words, the fans may be on and it also thinks it needs to heat because the thermostats are measuring slightly different because they may be slightly out of calibration or they're just recording a slightly different set of conditions. So this is something that we typically try to convince growers not to do. By the way, these thermostats are also not shielded and they are not aspirated. So they are perhaps getting false readings because of sunlight hitting them directly. They may also be seeing an occasional unintended spray of water when somebody is irrigating the crop. So this is not an ideal installation. And so this is another plug to try to convince you that computer control is more efficient and more beneficial so that you can make sure that things like running a ventilation system and a heating system at the same time are no longer occurring in your operation. I wanted to say a few more things about sensor location and sensor placement, as well as calibration. On the image in the left-hand side, you see a sensor that was kind of hastily put in place. It's not shielded, it's not protected. It may sense what the plant is observing, it may not. Again, this is not something what we recommend. On the right-hand side, you see a sensor system that is installed correctly. However, it is installed quite high. And if you look at the total picture, you see that the bulk of the crop is grown on the floor. And the sensor box, the aspirated box, is mounted close to the hanging baskets. So you may get a pretty good indication of what the hanging baskets are observing, but you probably will not get a good idea of the conditions experienced by the crop grown on the floor. So you want to think about placement, and then of course you want to regularly make sure that those sensors are calibrated and providing you with the correct information. There's no point in trying to have a sophisticated control system when the sensors are not recording the correct conditions in your operation. I wanted to also mention alternative fuels again. Here's an example of a grower who had a local source of shredded wood from a waste, from a paper processing plant. So this was a waste product for the plant. And the grower decided that this was a good resource to use as fuel for the heating system. Obviously, when you switch to a different fuel source, you probably have to do some modifications to handle that fuel. And here you see some examples of that. Conveyor system and what we call walking floor systems to process that shredded wood once it was delivered on site, to be able to feed it into a set of biomass boilers that then can produce, in this case, warm water for the greenhouse. And if you know anything about boiler systems, then you know that most boiler systems operate at what we call a sweet spot. And that sweet spot is typically close to the maximum output of a boiler system. That's how they are designed. And that means that we typically like to run those boilers as much as possible at that relatively high output level. And the grower that installed this system recognized that and decided that that was fine, but that might not always work, of course, with the demand that the greenhouse has for heating. And therefore, this grower thought it was a good idea to also install an insulated tank, a storage tank for hot water that was produced by the boiler, but not needed at that particular moment in the greenhouse. So in the image on the very left-hand side, you see a large yellow tank sitting next to the greenhouse. That's the storage tank. And that storage tank allows the boiler then to operate as much as possible at its sweet spot, at its highest efficiency, because whatever heat is needed in the greenhouse is delivered, and the excess heat that there may be is pumped into that insulated storage tank for later use. So by thinking through the process and by looking at where in the process we can gain efficiencies, this grower not only looked at alternative fuel sources, but also recognized that storage of hot water was important to try to maximize the efficiency of their system. Another area where we can focus on energy conservation is supplemental lighting. And one of the issues that I want to specifically address today is the type of heat that is being produced by high pressure sodium or LED fixtures. High pressure sodium lamps produce mostly radiant heat, so they are approximately 25 to 30% efficient in converting electricity into useful light, and the rest is heat, and that heat is in the form of radiant heat. That means that any surface in direct line of sight between the light source and the surface itself will receive that radiant energy. And there's not much we can do with that radiant energy unless it finally hits that surface. Then it will heat up the surface, and that in turn will heat up the surrounding air, and then we can deal with that warm air. But that radiant energy is otherwise very difficult to deal with as long as the lights are running. And so what happens, that can be an advantage in the wintertime when you want to heat your crop. You get some quote unquote free heat from the lighting system. However, it's not really free, because you're heating with electricity, and heating with electricity is very expensive. And the other thing that can happen is, especially in taller crops where you have multiple layers of leaves, the leaves on the top of the canopy are in direct line of sight to the light sources, and they will receive a radiant heat, but lower layers of leaves in the canopy may not are not maybe directly positioned in a direct line of sight, and therefore will not get that heat, and therefore you may get non-uniform heating in your crop. So growers, of course, have learned how to work with high pressure sodium lights, and they have been very successful doing that. But there are certainly some drawbacks to that particular system. And so a lot of us have been looking very carefully at the newer technology, the LED lamps, and they are very exciting. We can do a bunch of new things with them. And in this context, I particularly want to focus on the heat they produce. They produce not radiant heat, a little bit often, but not as much as the high pressure sodium fixtures. They produce convective heat. In other words, they produce hot air. And we know in greenhouses how to deal with hot air. We can move that with fans and exhaust systems to remove that from the system. So it's easier for us to deal with, and therefore we can typically place those lamps much closer to the crop, further reducing any light loss and improving the overall efficiency. But the point that I really want you to remember is that LED lamps still produce a fair amount of heat, and we still have to deal with it. It's just in a more convenient form for us to deal with than the radiant heat that high pressure sodium fixtures are producing. And then my little reminder on the bottom of the slide says that when you run your supplemental lighting systems, you do not want to forget about the CO2 concentration, because if the plants do not have enough carbon dioxide, they will not be able to photosynthesize, despite the fact that you are adding expensive light in the form of supplemental lighting on your crop. So you want to make sure that if you do light, that the plants have enough carbon dioxide to produce and perform photosynthesis. I want to go back to computer control a little bit more and hopefully impress upon you that that system is far superior to trying to do it manually, although it's not impossible to do it manually, but you have to have a dedicated person really that keeps an eye on things and makes adjustments, which is typically not something that we can afford in greenhouse operations. So of course we use sensors for that, and those sensors can keep track of multiple quantities, parameters we call them, that are happening: temperature, light, humidity, things like that, the carbon dioxide concentration. And typically those computers use a bunch of rules. Somebody decided that you wanted to maintain a certain temperature using a particular set of rules, and that is implemented in computer code in that computer system. And we call those rules sometimes algorithms, a bunch of rules that we have predetermined and incorporated in the software, and then the computer system implements those rules in order to give us what we hope the system is able to provide. And those algorithms can be tailored to a variety of different crops that can be adjusted for different seasons. For example, the change from the cooling season to the heating season. It can also incorporate different aspects of your facility, the size, the dimensions, the type of equipment you have inside, things like that. So it is really very broad in terms of the types of things you can do with a computer control system. And then these algorithms are typically designed to maximize things like quality or yield, and obviously minimize production costs. But on top of that, growers can implement additional rules that they feel are most appropriate for their operations. For example, in the wintertime when there is snow on the greenhouse, you may have a set of rules that turns on the heating system, especially the heating pipes near the roof, and it may open up the energy or shade curtain to try to get a lot of heat to that roof to melt that snow off as quickly as possible. Obviously, when you're not in an area with a lot of snow, that's not important to you, but if you are, then you may develop your own rules and you can implement those rules in that computer control system. The other advantage of computer control systems is that they can keep accurate records of what was happening. And when you combine those records with your plant observations, that set of information becomes very valuable for things like benchmarking, comparing this year's crop with last year's crop, so that you know how your crop is doing relative to a previous growth cycle. And you can also then figure out if it's still on schedule. Am I still able to make the target date? It can also be very helpful when you troubleshoot. When you had a malfunction sometime during the middle of the night, you can go back to that record and figure out, well, which section was the first sign of a problem, and exactly when did it occur, in order to try to help you figure out how to solve the problem. And then these records can be very helpful for planning purposes. For example, you can ask yourself, how did we do? And does that mean we should do it again when we plan our next growth cycle for the following year? And so my comment on the bottom says that yes, computer control systems are costing money, and they in some cases are not inexpensive, and they have a learning curve. You have to learn how to set them up, how to implement these rules, how to make sure they do what you expect them to do. But in the long run, they are very useful tools, and I think you will find that you can certainly optimize your production system very well when you have these tools at your disposal. So I recommend, if you don't already have it, to invest in a computer control system. What I'd like to do is summarize some of the energy savings that you may contemplate or that we have reviewed today. I want to start off with a disclaimer, though. The percentages that I list here for some of these processes or activities that you want to do are not additive. So you can't add all these or do all these various things and get to a number that is larger than 100%. These are numbers that indicate sort of the range of savings you may expect if you individually implement these. So the first one here says, before you do any changes to your system or any adjustments or modifications, always start with energy conservation first. That is typically the most cost-effective way of reducing your energy consumption and therefore improving your overall efficiency. But beyond that, if you are installing systems that require or need or could be improved by adding insulation, then you can see the savings of 2 to 5% are attainable, provided you use a high insulation value for the materials that you install. I mentioned timely maintenance already, and here you see 5 to 10% savings overall is not inconceivable if you have a solid maintenance program and you make sure all the equipment is maintained properly and in proper working order. We mentioned the energy shade curtain. Again, I think a 20 to 30% energy savings is not inconceivable. And that means that those systems are many times a no-brainer because they pay back for themselves very rapidly. And they probably last a lot longer than the payback period in many operations. I mentioned high efficiency heaters and boilers, and you see here you can significantly reduce your energy consumption by going that route. Even if you have fairly recently installed higher efficiency system, I recommend you go back to your supplier and ask what the latest specs are and see what further improvements are possible. You can use computer control systems and, as we mentioned, variable speed motors and pumps, again, for some savings. You can try to lower your set points, but again, I want to caution you that will have an impact on your crop, so you want to carefully think about that. You can also consider switching to higher efficiency lighting fixtures. We talked about that. Yes, the cost of LED fixtures is quite high, is still quite high, and in many cases much higher than HBS fixtures. So the initial capital expense is something that may be a hurdle, but after that, you can certainly reduce your electricity consumption quite significantly. And finally, if you are considering a new installation, I think it's a good idea to investigate cogeneration and see whether that has benefits for your operation. So what we're doing there is we are generating electricity on site, burning a particular fuel source, and that electricity is then used on site for our equipment, and in some cases is exported to the grid for additional income. And the cogeneration comes from the fact that we are also capturing the waste heat from that system. So the combustion of the fuel generates heat. We can run that exhaust gas through a heat exchanger, capture that heat in the form of warm water, and then use that to help us heat the greenhouse. And so some of these may sound kind of daunting, and some of those certainly are quite expensive, especially in terms of the initial capital expense. But what I would like you to consider is to try it on a small area first, if you can. See if you like it, see if it works for you, and then take the bigger leap and perhaps do a major upgrade. So always try something out first, I think, especially when you are looking at a fairly involved and fairly expensive process. I wanted to, at the end of my talk, give you some resources that I think are useful. The first one is Virtual Grower. It was developed by colleagues at the USDA. It's a tool that allows us to simulate for a particular greenhouse operation at a particular site, particular location, what the predicted fuel consumption will be, or energy consumption will be, depending on a variety of crops we grow. And so this is a nice tool for us to simulate what might happen in your operation and what might happen if you decided to, for example, change your fuel source or upgraded your heating system or installed an energy curtain. Those kind of questions you can ask using this calculation tool, and you can then make a more informed decision about what those changes would do in terms of your bottom line. So I think it's a very useful tool. It's a free download. It's currently in the version 3.1, and I know that colleagues at the USDA are working at the next version, version 4, which will be coming out, I hope, sometime this year. The other resource, especially when you're considering lighting issues, that I think is very useful is the book called Light Management in Controlled Environments. That was a book that was edited by colleagues at Michigan State, Roberto Lopez and Eric Runkle, who you probably are familiar with. And you can see here on the left-hand side, the topics that are covered in this book. It's a pretty broad range. It covers a pretty broad set of crops. So anytime you use supplemental lighting, I think you will find something useful in this book, and therefore it's a good resource to have. It's available on Amazon if you want to purchase it. So that concludes my presentation. I want to point out that the next webinar is going to come up soon. And I'd like to thank you for your attention, and I'm happy to answer any of the questions you may have. Thank you very much.
Hey, thank you so much, Dr. Booth. Both, I'd like to open the session up for Q&A now. Again, please submit your questions in the webinar chat or in the Q&A function. So, Dr. Both, looks like we have one question for you. For the HE unit heater, does the exiting cooler also act to warm the incoming combustion air?
Thanks for the question. That depends on the unit. There are some units where the design is such that the outgoing air is helping to heat the incoming air. Typically, that is not done because the outgoing air is cooled to a fairly low temperature, so it wouldn't help very much preheating that incoming air. So it depends on the design. If I would have to make a guess, I would say that most of them will not do it, but there are a few that I'm aware of that have that particular design.
Okay. All right, another question for you. After implementing energy conservation measures, what is one of the most common and effective strategies for reducing energy consumption in greenhouse operations?
That's another good question. Again, I want to emphasize what I said in the presentation, that energy conservation should be the very first thing you want to look at. You want to first investigate where and if you can conserve energy by changing your practices or maybe making some modifications to your systems. But after that, I think the topic that would be top on my list would be to look at an energy curtain to try to reduce heat loss during the night and during the colder times of the year. Typically, these systems are fairly easy to operate, and certainly when you have a computer system, it's a quick install and changeover, and the savings are significant, so that the return on that investment are typically fairly short. So in 3 or 4 years, you should be able to recover that investment, and then these systems, of course, will last longer than that. And at that point, you're just making money by having these systems installed.
Okay, thank you. At what point is growing crops cooler not a cost-effective method due to the longer grow times?
Yeah, that's another good management strategy question. When you start growing cooler, it's very likely, and I have to say that I'm not a plant scientist, I'm an engineer, so take my word for what it is. But typically when you grow your crop cooler, it will take the crop longer to mature to get ready for harvest. And so that means that you have to spend more money on keeping that crop in your facility longer. You're saving by reducing your energy inputs, but you may, because of the extra time, have extra expenses. So this is something you have to carefully weigh and carefully figure out. And typically these decisions are very site specific because of the different management strategies, the different crops people grow. So it's not a quick and easy answer. It's something that is crop specific, site specific, and management strategy specific. And it's something that individual growers typically discover over time and then realize what they need to do in order to be as efficient as possible.
Okay, cool. Can you speak about the benefits of inflated double poly?
Sure. The inflated double poly system was something that was invented by my predecessor at Rutgers University, who came up with the idea after people started experimenting with a single layer of plastic film that was developed in the early 60s of the last century as a way to cover greenhouses. It was a relatively inexpensive material that allowed light to go through, but of course was not very good, just as glass is, at keeping the heat inside the facility. And so just like the idea of double glazing, which we see often in commercial and residential buildings that helps reduce the heat loss, the idea that my predecessor came up with, and that is the double layer inflated polyfilm system, is intended to increase the insulation value of the glazing material. Now, this is not a very significant increase, but it's enough to make it feasible and economical for greenhouse operators to install this system. And so you are reducing the heat loss, and therefore you're saving energy when you have this double inflated system. And the inflation is typically done with a small fan that runs 24 hours a day and usually brings in outside air for the inflation purposes. And the reason we recommend using outside air is that outside air is typically drier than inside air because plants transpire and create lots of water vapor inside the greenhouse. So by using the drier air, we have less chance of condensation forming between the two layers when that air cools, because that condensation could impact the light transmission of the system. So the two layers are good for added insulation, and use outside air to try to limit or reduce the potential for condensation between the layers.
Okay, thank you. That's really cool. So do you have any suggestions on how growers can properly budget for energy prices or lock in low rates early?
Yeah, there are certainly growers that are very keen on following the market and try to lock in prices. Now, that may or may not be easy to do. In some cases, you may need to have storage capabilities on site. And not everybody, of course, has those facilities on site. If you wanted to buy a liquid fuel during the summer months because it was cheaper, then it probably is going to be delivered during the summer months, and you have to store it from the summertime to the wintertime when you may use it. So that is an added cost and an added concern, because you need to install the equipment and you need to make sure fuel doesn't leak, etc., and is available when you need it. But it's certainly a smart idea to try to lock in prices during times of the year or over years when prices are low, to then have lower priced fuel when you need it during the wintertime. So try it if you can. If you can't, you're more susceptible to those fluctuating prices. And then I think it is a good idea to regularly review the type of fuel you're using and figure out if at some point it may make financial sense to consider switching to an alternative fuel source. And again, that's going to come with additional costs. You probably have to do some changeovers and perhaps equipment replacements and modifications. But if you calculate it out over some years into the future, you should be able to tell whether that investment and that changeover makes sense in the long run.
Okay. How long can hot water stay hot for in excess reservoirs when using boiler systems?
Also a very good question. That depends on the insulation value of the system. We can insulate these systems to a large extent to where they can maintain their temperatures almost indefinitely. But in that case, we need very thick walls with very thick layers of insulation that makes the system more expensive. So as engineers, we make trade-offs. And we want to make these systems affordable to growers to install and use, but we also want to have a decent amount of energy retention so that heat is not lost very quickly. So you have to weigh the pros and cons. Yes, we want to store that heat as long as possible, but if we store it very long, we probably have to use a very expensive system. So we compromise and we come down somewhere in the middle. So we have systems that do a decent job in conserving that heat energy and do that at a reasonable price.
Okay, thank you. What do you think about geo-exchange as an option for commercial greenhouses?
Yeah, I think the question is about geothermal energy, trying to extract heat energy from the soil, use the soil as a reservoir during the summertime to get rid of that heat when we have warm greenhouses, and in the wintertime extract heat from the soil and bring that into the greenhouse for heating purposes. Those systems have been used in other industries quite extensively, in residential and commercial buildings, for example. these systems are available and companies do these installations. I've done some research on this and discovered that we can further improve the efficiency if we have, again, insulated storage tanks to try to buffer the availability of the heat with when we need it and how we need it. But it's not something that we see a lot being considered for commercial greenhouse operations. And the reason is that in greenhouse operations, we typically need something that is highly reliable and can deliver a fair amount of either heating or cooling. And if you try to combine that with these ground source heating systems or cooling systems, you recognize that in most of the time, these systems are, while good for energy savings, they are not able to deliver large quantities very rapidly. And so I think more research is needed to make sure we can optimize these systems for greenhouse operations, but currently we don't see a lot of commercial installations going that particular direction.
Okay. Let's see. Okay, it looks like we have one more question for you. Let's see, why are temperature and humidity sensors typically installed inside an aspirated box?
So we want to measure the temperature and the humidity and other parameters carefully, and we want to get the right number. And if we don't put a temperature and humidity sensor, for example, in an enclosure to shield that sensor from solar radiation, we could read false high readings. And of course, with those readings, then the control system makes the wrong decisions, and in some cases that can result in significant additional energy consumption. So we like to put sensors as much as we can inside an enclosure to shield them from, for example, solar radiation. And in addition, if we do so, we also shield those sensors from an occasional splashing when somebody is careless with the watering wand or with the irrigation system, and that sensor could get wet. And in some cases, again, that wetness eventually will dry out, but could affect the reading and therefore could affect the control system and therefore the energy that is needed for maintaining the right set points.
All right, let's see. Any other questions anybody might have? Okay. All right, well, it looks like that's all. Oh, someone raised their hand. I don't know. Okay, they're gone. All right, well, it looks like that's all. So thank you for joining us for another session of AFE's Grow Pro webinar series. Join us on February 28th, 2023 at 1 p.m. for our next session on success with vegetative unrooted cuttings. Visit endowment.org/GrowPro to see our full list of upcoming sessions, past webinar recordings, other grower-related resources, and research reports, all of which are available to you free thanks to industry support. We also ask that you please complete the brief survey about today's session where you can suggest additional topics and help us continue to improve these webinars. Thank you again for joining us. Thank you, Dr. Both.
Thanks, Karen, and thanks everybody for listening and participating. Bye-bye.
Bye.